Okay, so the purpose of Lab 4 was to implement the simple function and its inverse. As I will explain in my lab report, I didn't actually have enough time to completely implement either the FPGA board or successfully debug the inverse. I have code for the inverse, but something's not working, and I suspect that the issue is in the initial step here where I'm trying to subtract the S key value from A or B, whichever one. I just think there's an issue there, but I'll include the code, and I've explained kind of the issues I had here in the forward, but I also drew out the FPGA implementation diagram because I was intending to implement it. I just kind of ran out of time here. So actually let me show on paper because it's probably going to be easier to see it here. So the idea was that for our FPGA board, we take in the clock, so the 100 megahertz clock, 16 switches, and then 2 buttons. I also was including my clock divider module, which I used in the last lab. It just outputs a divided clock so that we can actually see the inputs. Or we would actually be able to see each of the rounds, the different inputs as they go through, about a second apiece. So yeah, the divided clock then goes into the RC5 encryption module. And I also know that this is only the simple function, it's not the true encryption, but I named it that in case I wanted to expand later. And let's see, so the clear bit will obviously be one of the inputs for RC5. The input val, inp val here, this value, is actually meant to mean whether or not the input's valid. So the idea is that from the FPGA board, since we have 16 switches and we need to get 64 inputs, and we also need one of those switches to be for the clear. One is for the clear, always, and then we can use the other 15 for taking the inputs in, and then one of the buttons. So basically, when you push the button the first time, it'll put 15 into the input that we're going to use in the encoder module, into the DIN that we're going to use. And then it'll do 15 and 15 and 15, and that leaves 4 bits left, and then so the 5th push will do 4 bits. And so once the button's been pushed 5 times, it should set this input valid value equal to 1. This is sort of a way of building a finite state machine without it being like a true, finite state machine. But yeah, that would make it so that this would only actually start incrementing the counter and performing if it had actually already gotten a full input given to it. And then, then there's an output here. This is the 64-bit output. After the 12 rounds, well, you would see it each round, but after the 12 rounds, it would be displayed on LEDs, which there are 16 of, and then that's where the second button helps, because then we would use that button to view each of the different sets of 16. So yep, hopefully that makes it clear. Sorry that I don't have the full FPGA implementation, but just kind of ran out of time here. Okay, alright, thanks for watching.